Hello, my name is Ophir. I'm the inventor of the Dosi method. Dosi stands for Differential Optical Spectropolarimetric Imaging. So let's see how the scanner works. Let's say I have a skin lesion and I want to scan it with our scanner. So we have four stages. The first one, light is transmitted to a lesion in various angles of illumination, assisted with polarizer number 1. The polarizer actually changed the direction of the oscillation, and by changing this direction, the backscattered light will generate a bit different images. So for each change, I'm capturing here a frame. The light is bounced back from the lesion in two ways. One is from the superficial surface, which is less interesting for us because the distortion underneath the skin that can end in cancer is underneath the lesion. So we would like to understand what's happened here. Another feature or virtue of this specular light is the oscillation of the light is just like the source, so it's not interesting for us, but we can use it to block it. The second information that will be allowed to go to the camera is the deeper layers, and the deeper layers generate some other polarization that can be transmitted by the second polarizer. So the second polarizer is blocking the superficial surface but allowing the underneath information to go to the camera. So for each illumination angle here, Dosi takes a snapshot assisted with polarizer number 2 to block the superficial information, the superficial light here, this marked in green. Then finally we end with a sequence of images. So each image, it's a picture when the state of polarization was different. So we have more or less the same picture, but still there are small changes between each frame. So through our algorithms, we can reveal small differences between images. Now, a healthy area, which transmits more or less the same light, will appear in black, and a distorted area that behaves different to a different state of polarization will emerge as in grayscale, will emerge more white, and by that we can follow the underneath distortion. It's very important to understand what happened underneath the skin much before the pigmentation appears, and sometimes it's too late. So how it looks like in our prototype. Here is the transmitted light marked here with different wavelengths. This yellow tubes, it's just the tube of light. Then we stick here the lesion. The polarizer here set the polarization of the light, and we have, you cannot see it here, but I'll show you later, in the middle you have the second polarizer that transmits the light through the lens and through the camera, and then here we have some electronics that I'm not indicated it here. So again, we have polarizer and transmitted light. Here it is over here. We have another polarizer that block the specular light. It's somewhere here, and then from here to the camera we have this light path that's marked here in gray. Let's see how it looks like. So this is the machine. Let's see it from above. You'll see here the light path, the polarizer, and the lens. Okay, now you see it, and let's see it from the side. So you will see The user stick the lesion over here. Here is the light. Here is the polarizer that's changing. You can see it here. You can see the polarizer here changing. In the middle, we have another polarizer that able to transmit or to block actually the specular light. So for each angle of polarization, we see here the information underneath the skin. And then the camera gather the whole information, and from now on the computer is doing the process of understanding the underneath distortion. So finally, I can give you here some example. So this is the prototype. This is the controller, the electronic controller I built, and you can see here the light source. Here the lesion supposed to be situated, and another polarizer that block the information and allow the underneath information to go to the camera. And from here, the computer is doing the rest of the job to understand underneath distortions. So here some example. This is a wide view of a lesion. This is the image taken by dermatoscope, for example. So it's a simple image, but just a small part of this lesion. And you see here that the algorithm, the Dosi algorithm, I won't get into it too much here, but various Dosi algorithms can produce information about the underneath distortion. So you see, what we see in our bare eyes is not necessarily what happened underneath the skin. Now, if underneath distortion can deteriorate to cancer, it will be very important to understand that it actually exists. And sometimes just by looking at bare eyes, one cannot understand if the lesion is distorted or not, or if it's developed over time and deteriorate over time. Thus, we think that the solution we are offering can be a good way to understand what happened underneath the skin, and by that save life.